The enigmatic abyss, a deep dive into black holes. Introduction. Black holes are among the most fascinating and mysterious objects in the universe. They warp space and time, trap light, and challenge our understanding of physics. In this comprehensive exploration, we will delve into their formation, properties, types, and the profound implications they have on cosmology. By the end, you will have a thorough understanding of these cosmic enigmas and perhaps even more questions than when you began. Chapter 1. What is a black hole? A black hole is a region in space where gravity is so intense that nothing, not even light, can escape its pull. This occurs when matter is compressed into an extremely small volume, creating a gravitational singularity. The key concepts of black holes, a detailed exploration. Black holes are among the most extreme and enigmatic objects in the universe, where gravity dominates all other forces and the laws of physics as we know them break down. To truly understand them, we must examine their key concepts in depth, including their history, theoretical foundations, and technical details. 1. The event horizon, the point of no return. Definition and significance. The event horizon is the boundary around a black hole beyond which nothing, not even light, can escape. It is a one-way membrane. Once crossed, there is no return. Mathematical description. For a non-rotating black hole, the event horizon radius, Schwarzschild radius, Rs, is given by Rs equals /c squared, where G equals gravitational constant, M equals mass of the black hole, C equals speed of light. For a rotating black hole, the event horizon is oblate due to spin. Historical insight. First rise by Carl Schwarzschild as a solution to Einstein's field equations. Latter refined by Roy Kerr for rotating black holes. Observational evidence. The Event Horizon Telescope captured the first image of a black hole shadow, confirming the event horizon's existence. Minus 2. The singularity, where physics breaks down. Definition and nature. At the singularity, density becomes infinite, spacetime curvature is undefined, and general relativity fails. Types of singularities. 1. Space-like singularity. A. Point at the center. 2. Ring singularity. A. Spinning ring where centrifugal forces prevent infinite compression. The problem with singularities. General relativity predicts them, but quantum mechanics suggests they cannot exist. A theory of quantum gravity may resolve this. Historical debate. Einstein himself doubted black holes could form. Penrose and Hawking proved singularities are inevitable under general relativity. Minus 3. Gravitational time dilation. Time slows near a black hole. Einstein's prediction. Time runs slower in stronger gravitational fields. Near a black hole, time almost stops at the event horizon. Mathematical formulation. The time dilation factor is given by T0 equals Tf, where T0 equals time experienced by an outside observer. Tf equals time experienced near the black hole. R equals distance from the singularity. Practical implications. If you watch someone fall into a black hole, they would appear to freeze at the horizon. However, from their perspective, they would cross the horizon normally. Minus 4. Hawking radiation. Black holes can evaporate. Stephen Hawking's discovery. Quantum fluctuations near the event horizon cause particle-antiparticle pairs to form. When a particle falls in, the other escapes, leading to energy loss. Mathematical description. The Hawking temperature of a black hole is Th equals h bar c caret 3 backslash, where h bar equals reduced Planck constant, kV equals Boltzmann constant. Implications. Smaller black holes evaporate faster. Over 10⁻100 years, even supermassive black holes will evaporate. Minus 5. The information paradox. Does information disappear? The problem. Quantum mechanics says information cannot be destroyed. Viewed if a black hole evaporates via Hawking radiation, what happens to the information of consumed matter? Proposed solutions. 1. Hawking's original view. Initially, Hawking believed information was destroyed, violating quantum mechanics. 2. Holographic principle. Proposed by Gerard T. Hooft and Leonard Susskind. Suggests information is encoded on the event horizon. 3. Firewall paradox. A wall of energy at the horizon that destroys invalid objects. Current status. The debate continues, with string theory and quantum gravity offering possible resolutions. Minus 6. Spadification, tidal forces near a black hole. What happens when you fall in? Tidal forces stretch you vertically and compress you horizontally. For stellar mass black holes, this happens before crossing the horizon. For supermassive black holes, you might cross the horizon before being torn apart. Mathematical explanation. The tidal force difference is delta A equals delta L, where delta L is the length of the object. Conclusion: why these concepts matter. Understanding black holes pushes the boundaries of general relativity, quantum mechanics, and cosmology. They are not just cosmic curiosities, they are keys to unifying physics and unlocking the universe's deepest secrets. Further study. Books: The Black Hole War, Black Holes and Time Warps. Research papers: Hawking's original 1974 paper, Penrose's Singularity Theorems. Documentaries Into the Universe with Stephen Hawking. Chapter 2. Formation of Black Holes. An educational and informative exploration into one of the universe's most mysterious phenomena. Minus. Introduction. Black holes are among the most enigmatic and fascinating objects in the universe. They are regions in space where gravity is so intense that nothing, not even light, can escape. The idea of black holes was first derived from Einstein's theory of general relativity, but it took decades of observation, research, and technological advancement to confirm their existence. This chapter explores in detail the formation of black holes, delving into the physics of stellar death, gravitational collapse, different types of black holes, and the cosmic implications of their creation. Minus. What is a black hole? Before understanding how black holes are formed, it is essential to understand what they are. A black hole is a point in space where the gravitational pull is so strong that not even electromagnetic radiation can escape from it. The boundary surrounding a black hole is called the event horizon. Once anything crosses this boundary, it cannot return. At the center of a black hole lies the singularity, a point of infinite density where the known laws of physics break down. The formation of this singularity is a result of the extreme gravitational collapse of matter. Minus. Stellar evolution and black hole formation. The story of a black hole begins with a star. Stars are massive balls of plasma undergoing nuclear fusion, converting hydrogen into helium and producing energy. A star remains stable because of the balance between gravitational force pulling inward and radiation pressure from fusion pushing outward. However, this balance is temporary. Life cycle of a star. 1. Protostar phase. A star forms from a cloud of gas and dust that collapses under its own gravity. 2. Main sequence star. The star begins fusing hydrogen into helium. The Sun is currently in this phase. 3. Red giant or supergiant. Once hydrogen is depleted, the star begins to fuse heavier elements. The star expands significantly. 4. End of fusion. The fusion process halts when iron is formed, as iron fusion requires more energy than it releases. Once nuclear fusion stops, the star is no longer able to resist its own gravity. What happens next depends on the initial mass of the star. Minus. Pathways to black hole formation. 1. Stellar mass black holes. Stars with a mass greater than about 20 to 25 times the mass of the Sun end their lives in a spectacular explosion called a Type II supernova. This explosion blows away the outer layers of the star, while the core collapses under gravity. If the remaining core is between 1.4 and 3 solar masses, it may become a neutron star. If the core is more massive than about 3 solar masses, gravity overwhelms all known forces and the core collapses into a black hole. This process can happen in a matter of seconds, but it results from millions of years of stellar evolution. 2. Direct collapse. In some very massive stars, a supernova might not even occur. Instead, the star may collapse directly into a black hole without any explosion. This is known as direct collapse and is a leading theory for the formation of early, massive black holes in the universe. 3. Mergers of neutron stars. Two neutron stars orbiting each other can eventually merge due to gravitational radiation. The merger can create a more massive neutron star, or a black hole often accompanied by a gamma-ray burst. 4. Primordial black holes. These are theoretical black holes that could have formed just after the Big Bang, due to extremely high densities and fluctuations in the early universe. Unlike stellar black holes, they are not the result of star death. Minus. Stages in the formation of a stellar black hole. Let us look deeper into the stages of stellar black hole formation. A. Collapse of the core. As the iron core of a massive star reaches the Chandrasekhar limit, it can no longer support its own weight. Electrons and protons combine to form neutrons and release neutrinos. This sudden collapse is incredibly fast, occurring in fractions of a second. The supernova explosion. The outer layers are expelled violently into space due to the bounds caused by the core collapse. This is seen as a supernova, one of the brightest events in the universe. See formation of the event horizon. If the collapsing core is massive enough, it compresses beyond the Schwarzschild radius, forming an event horizon. Inside this boundary, all paths lead inward, forming the black hole. The singularity formation. At the very center, the matter collapses into a point of infinite density, where time and space cease to behave normally. This is the singularity. Minus. Types of black holes based on formation. Black holes can be classified not just by their size but also by how they form. 1. Stellar mass black holes. Formed from collapsing stars. Mass 3 to 100 times that of the Sun. Found throughout galaxies. 2. Intermediate mass black holes. Possibly formed from the merger of smaller black holes or through direct collapse of massive gas clouds. Mass 100 to 100,000 solar masses. Rare and difficult to detect. 3. Supermassive black holes. Found at the centers of galaxies. Mass millions to billions of solar masses. Likely formed through a combination of processes, accretion of matter, mergers, and early universe direct collapse. Our Milky Way has a supermassive black hole named Sagittarius A. 4. Primordial black holes. Hypothetical, formed in the early universe. Could be microscopic or massive. Might account for some dark matter if they exist. Minus. Factors influencing black hole formation. 1. Initial mass of the star. More massive stars are more likely to form black holes. 2. Metallicity. Stars with fewer heavy elements lose less mass through stellar winds and are more likely to end as black holes. 3. Rotation and magnetic fields can influence how material collapses. 4. Environment. Stars in dense clusters are more likely to interact or merge, potentially leading to black hole formation. Minus. Black holes in the cosmic context. Black holes play a vital role in shaping galaxies, star formation, and even cosmic evolution. For example, supermassive black holes regulate star formation by ejecting energy and material. Merging black holes create gravitational waves, ripples in spacetime first detected in 2015 by LIGO. Accretion disks around black holes can shine brightly in X-rays, helping us locate them. Minus. Observing black hole formation. Although black holes cannot be observed directly, their formation and presence can be inferred through Gravitational waves. X-ray emissions. Supernova observations. Stellar motions around invisible objects. Shadow imaging. Conclusion. The formation of black holes is one of the most profound outcomes of stellar evolution and cosmic dynamics. From the quiet death of a giant star to the explosive merging of neutron stars, black holes emerge as natural results of gravity's relentless pull. They are not just cosmic vacuum cleaners or mysterious voids, they are essential components of the universe's architecture. As our tools and understanding improve, we continue to peel back the layers of mystery surrounding them. With missions like the James Webb Space Telescope, LIGO, and future gravitational wave observatories, we may one day witness a black hole forming in real time, a true marvel of nature and physics. Key terms recap. Event horizon, the boundary around a black hole. Singularity, the point of infinite density at the black hole center. Chandrasekhar limit, the mass limit beyond which white dwarfs collapse. Supernova, a massive explosion ending a star's life. Stellar evolution, life cycle of stars leading to different endpoints. Schwarzschild radius, the radius defining the size of the event horizon. Chapter 3, types of black holes. Not all black holes are the same. They are classified by mass and properties. 1. Stellar mass black holes. Formed from dying massive stars. Often found in binary systems, emitting X-rays as they consume companion stars. 2. Intermediate mass black holes. Rare and poorly understood. Possibly formed from merging stellar mass black holes. 3. Supermassive black holes. Reside at the centers of galaxies. Origin nuclear may form from direct collapse of giant gas clouds or repeated mergers. 4. Theoretical, micro-black holes and wormholes. Quantum black holes would evaporate via Hawking radiation. Wormholes, if real, could be shortcuts through spacetime. Chapter 4, how do we detect black holes? An educational, informative, and detailed exploration. Black holes are among the most mysterious and fascinating objects in the universe. Although they were predicted by Einstein's theory of general relativity over a century ago, their detection has always been a great challenge for astronomers. This is because black holes, by definition, do not emit light. Their gravity is so strong that not even photons, the particles of light, can escape once they cross the event horizon, the boundary beyond which nothing returns. So, how do scientists detect something that is literally invisible? The answer lies in indirect detection, observing the effects black holes have on their environment. In this chapter, we will explore the many ingenious methods astronomers use to discover and study black holes. From watching stars dance around invisible partners to catching ripples in the fabric of space-time. 1. Detecting black holes through stellar motion. One of the earliest methods of detecting black holes is by observing their gravitational effects on nearby stars or gas clouds. A black hole may not be visible itself, but the way it influences the motion of nearby objects can give away its presence. Binary systems. In many cases, black holes exist in binary star systems, pairs of stars orbiting around a common center of mass. If one of the stars is a normal, visible star and the other is unseen, astronomers can measure the visible star's orbit. If calculations show that the visible star is orbiting an unseen companion with a mass greater than about 3 times the mass of our Sun, and no light or radiation is coming from it, then it's likely a black hole. This technique led to the discovery of the first stellar mass black hole, Cygnus X1, one of the strongest X-ray sources in the sky. The visible star's motion showed it was orbiting an unseen, massive companion, later identified as a black hole. 2. Accretion disks and X-ray emissions. When matter falls toward a black hole, it doesn't just disappear instantly. Due to conservation of angular momentum, the infalling material spirals inwards, forming an accretion disk, a swirling, flattened structure of hot gas and dust. As material in the accretion disk accelerates and compresses due to the immense gravitational pull, it heats up to millions of degrees. At these temperatures, it emits X-rays and other high-energy radiation. These emissions are detectable using space-based telescopes like Chandra X-ray Observatory, XMM Newton, NuSTAR. This X-ray radiation gives us a clear signal of matter interacting with a black hole. Many black holes discovered so far have been detected this way. -3. Gravitational lensing. Einstein predicted that gravity could bend light, and black holes, being extreme gravitational objects, can act as cosmic lenses. When light from a background star or galaxy passes near a black hole, the light gets bent and magnified. This phenomenon is called gravitational lensing. While gravitational lensing can be caused by any massive object, an unusually strong lensing effect, especially if no object is visible in the foreground, could hint at a black hole's presence. In 2022, NASA announced the possible discovery of a rogue black hole using gravitational microlensing, a smaller version of lensing that can happen when a stellar mass black hole passes in front of a background star and briefly brightens it. -4. Gravitational waves. The most exciting and direct method of detecting black holes in recent years is through gravitational waves, ripples in the fabric of spacetime itself. When two black holes orbit each other and eventually merge, they send out gravitational waves that spread across the universe. These waves were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory. This marked the beginning of a new era in astronomy. Since then, dozens of black hole mergers have been observed through this method, confirming the existence of many previously unknown black holes. Gravitational wave detectors like LIGO, Virgo, and CAGRA continue to expand our understanding of the black hole population in the universe.